Welcome to Streamberg Space Stories. This is a place for calm, for curiosity, and for the kind of thinking that only happens when the world gets quiet. Tonight, we continue the story we began in Part 1. If you listened to Mission Mars: The Preparation, you heard about everything that must be solved before anyone can leave for Mars. The radiation, the food, the air, the silence. All of it tested, debated, refined across decades of patient work. But now, the preparation is over, the hatch is closed, and everything that comes next belongs to the journey. This is Part 2, The Journey. There is a morning, somewhere in the future, when 6 people will lie on their backs inside a spacecraft, strapped into seats that are tilted slightly so that the force of launch pushes through their chests rather than from head to toe. It is a deliberate design. The human body can tolerate far more acceleration in the chest-to-back direction than it can vertically. Fighter pilots, pulling out of a steep dive, can lose consciousness at 6 or 7 G when the force runs from head to foot. But lying down, with the force distributed across the back, trained individuals have endured more than 10 G while remaining alert. The crew will not face anything that extreme, but what is about to happen will test their bodies in ways that no amount of centrifuge training can fully replicate. The final minutes before launch are surprisingly still. The crew has been inside the vehicle for hours. They have run through checklists, confirmed pressures, verified seals. The world outside is loud with machinery and procedure, but inside the capsule the sounds are muffled. There is the hum of environmental systems, the whisper of circulated air. Heart rates are monitored, blood pressure is tracked. Each crew member wears a biomedical harness that streams data to flight surgeons on the ground. And then, at some designated second, the engines ignite. The sensation does not arrive all at once. At the moment of liftoff, the acceleration is modest, perhaps 1.5 times the force of gravity. The crew feels heavier, pressed gently into their seats, but the experience is not yet dramatic. The rocket clears the tower. It rolls to its programmed heading. Within the first minute, the vehicle passes through the region of maximum aerodynamic pressure, known as max Q, the point at which the combination of speed and atmospheric density creates the greatest stress on the vehicle structure. The engines may throttle down briefly to reduce the load, then throttle back up once the danger has passed. Within the first 2 minutes, as the boosters burn, that force climbs steadily. It reaches roughly 3 times normal gravity. Breathing becomes deliberate. Each inhale requires conscious effort, as though a weight has been placed on the chest. Limbs feel dense. Raising a hand to flip a switch demands real intention. Speech comes in short, compressed phrases. The crew has trained for this. They know the feeling, but knowing does not make it easy. Then the boosters separate, and for a brief disorienting moment the pressure drops. The body, having adjusted to the compression, suddenly feels light. But this pause is short. The main engines continue to accelerate the vehicle, and the force builds again. As fuel is consumed and the vehicle grows lighter, the same thrust produces greater acceleration. In the final moments before engine cutoff, the crew may experience close to 4 times normal gravity. NASA typically limits sustained acceleration to around 3.5 G, but even at that level, the experience is profound. Vision narrows, the world feels compressed, time itself seems to thicken, and then, all at once, it stops. The engines cut off, and the force that has been pressing the crew into their seats vanishes completely. Objects that were heavy become weightless. Anything unsecured drifts. The transition is instant and absolute. The inner ear, which moments ago was being crushed under triple its usual load, now receives no gravitational signal at all. For many astronauts, this transition is the most disorienting moment of the entire mission. The body does not understand what has happened. The stomach floats. The sense of up and down dissolves. More than half of all astronauts experience nausea in the first hours of weightlessness. It is called space adaptation syndrome, and it typically resolves within 2 to 4 days. But for those first hours, the extraordinary achievement of reaching orbit is accompanied by the very ordinary sensation of feeling seasick. The crew is now in low Earth orbit, but they're not yet on their way to Mars. There may be days of orbital preparation ahead, equipment checks, system verifications, perhaps a rendezvous with a transit vehicle or a refueling stage. The spacecraft that carried them off the surface of Earth may not be the same one that carries them to Mars. The architecture of a Mars mission is still being defined, but most proposals involve assembly or docking in orbit before the long transit burn begins. And so, for a time, the crew floats above the planet they're about to leave. They can see it through the windows, the blue curve of the atmosphere, the familiar shapes of continents, the thin luminous line of the horizon where the atmosphere meets the blackness of space. Every 90 minutes the spacecraft completes another orbit, and the crew watches another sunrise, another sunset. It is still close, still reachable. An abort at this stage would bring them home within hours. Then comes the Trans-Mars injection burn. The engines fire again, and the spacecraft accelerates beyond Earth's gravitational hold. This burn is quieter than the launch. The forces are gentler, but what it represents is absolute. Once the burn is complete, the crew is on a trajectory that will carry them away from Earth for the next 7 to 9 months. There is no turning around, there's no quick return. The mathematics of orbital mechanics do not allow it. The path to Mars is an arc, a long curving ellipse through the inner solar system, and once you're on it, the only destination is Mars. In the hours after the burn, the crew may look back at Earth and see it already shrinking, a blue disk growing smaller, the moon visible nearby, a grey companion in the darkness. Both will diminish, both will recede, and the space ahead, the direction the vehicle is travelling, will look exactly like the space behind. Stars in every direction, no landmarks, no signposts, just the slow, silent drift of a small machine through an incomprehensibly vast emptiness. The scale of interplanetary space is difficult to comprehend. On Earth, we measure distances in kilometres, occasionally in thousands of kilometres. The flight from London to Sydney, one of the longest commercial routes, covers roughly 17,000 kilometres. The distance from Earth to Mars at its closest approach is more than 3,000 times farther. At its most distant, the gap widens to over 23,000 times that flight. The spacecraft travels quickly, at tens of thousands of kilometres per hour, but even at that speed, the journey takes months. The cosmos is not empty in the way that a desert is empty. It is empty in a way that has no analogy in human experience. There's nothing out there, no air, no sound, no weather, no life. Just distance, measured in units so large that the human mind can hold them only as abstractions. And yet, inside the spacecraft, life continues. People eat breakfast, they argue about music, they forget to replace a filter, they tell the same joke for the 3rd time. The vastness outside is absolute, but the human world inside is small and particular and alive. This is perhaps the strangest thing about interplanetary travel, the contrast between the infinite emptiness of space and the relentless intimacy of human life within it. 6 people in a metal tube, surrounded by nothing, doing laundry and checking pressure gauges and wondering what their families are having for dinner. The route a spacecraft takes from Earth to Mars is not a straight line. It cannot be. Both planets are in motion, orbiting the Sun at different speeds and different distances. Earth moves at roughly 30 kilometers per second. Mars, farther from the Sun, travels at about 24. To travel between them, a spacecraft must be placed on an elliptical orbit that begins at Earth's distance from the Sun and ends at Mars's distance. This is called a Hohmann transfer orbit, named after the German engineer Walter Hohmann, who described it in 1925. It remains the most fuel-efficient way to reach another planet, and despite nearly a century of advances in propulsion, it is still the trajectory that most Mars mission concepts are built around. The transfer orbit carries the spacecraft roughly halfway around the Sun. The journey takes between 6 and 9 months, depending on the specific alignment of the planets at the time of departure. This alignment only occurs once every 26 months. Miss the window, and you wait more than 2 years for the next one. The precision required is extraordinary. The spacecraft must depart Earth at exactly the right moment, so that when it arrives at Mars's orbital distance some 250 days later, Mars is actually there to meet it. It is often compared to throwing a dart at a moving target while standing on a spinning platform, except the dart takes 8 months to arrive, and the target is a planet moving at 86,000 kilometers per hour. During the transit, the spacecraft is not powered. After the initial burn, the engines fall silent and the vehicle coasts. It follows the curve of its orbit the way a stone follows the arc of a throw. Gravity does the rest. There may be small course corrections along the way, brief firings of maneuvering thrusters to adjust the trajectory by fractions of a degree. These mid-course corrections are essential. Even a tiny error at departure can translate into a miss of thousands of kilometers to arrival. But the corrections are small and infrequent. For the vast majority of the journey, the spacecraft is simply falling through space, carried along by the geometry of the solar system. There is no sensation of movement, no wind, no vibration. The only evidence of motion is the slow shift of the Sun and the planets against the background of stars. The vehicle that carries the crew to Mars will be, for the duration of the transit, the entirety of their world. Its dimensions will define the boundaries of their existence. Current proposals suggest a habitable volume of roughly 100 to 200 cubic meters for a crew of 4 to 6. To put that in perspective, a modest studio apartment is about 40 cubic meters. The spacecraft is larger, but much of its volume is occupied by equipment, storage, and systems infrastructure. The actual living space, the area where the crew sleeps, eats, exercises, and socializes, is closer to the size of a small house. Except this house has no windows that open, no door to the outside, and no room to walk more than a few steps in any direction. Noise is a constant companion. The spacecraft is filled with the sound of fans, pumps, compressors, and life support machinery. These systems are essential, but they are never silent. On the International Space Station, noise levels in some modules have been measured above 70 decibels, equivalent to a vacuum cleaner running continuously. Sleep is disrupted. Conversations require raised voices. Over months, this background roar becomes a source of fatigue and irritation that is easy to underestimate. Future transit vehicles will be designed with better acoustic insulation, but some level of mechanical noise is unavoidable. This silence of space is an abstraction. Inside the vehicle, it is never quiet. Privacy is limited. Crew members will have individual sleeping quarters, small alcoves or pods that can be closed off, providing a few cubic meters of personal space. These are sanctuaries. Studies of long-duration isolation have consistently found that access to private space is critical for psychological health. In the tight quarters of a submarine, in Antarctic winter overstations, in the Mars 500 simulation, The ability to withdraw, even briefly, from the presence of others has been identified as one of the most important factors in maintaining morale and preventing interpersonal conflict. Personal items are carefully curated. Each crew member is allocated a small mass allowance for personal effects, photographs, books, a musical instrument perhaps, a favourite flavour of coffee. These objects, trivial in other contexts, become profoundly important in isolation. They are tangible connections to the life the crew has left behind, physical reminders that the world they came from still exists, even as it shrinks to a point of light. What does a Tuesday look like in month 4? This is, in many ways, the central question of the journey. Not what the spacecraft can do, but what the people inside it will do. How they will fill the hours, how they will maintain their health, their purpose, their sanity, in a metal container surrounded by the same 5 faces for more than 200 days. The schedule is structured down to the hour. It must be. Without structure, the days become formless, and formlessness is dangerous in confinement. The crew wakes to an artificial light cycle designed to mimic the progression of a day on Earth. Circadian rhythm disruption was one of the most consistent findings in the Mars 500 experiment, where 4 of 6 crew members experienced significant sleep disturbances. On a real transit vehicle, the lighting systems will shift in colour and intensity throughout the day, from bright blue-white in the morning to warm amber in the evening, trying to give the body the cues it no longer receives from the sun. Exercise takes up at least 2 hours each day. This is not optional. It is a medical necessity, as essential to the mission as fuel or oxygen. In microgravity, the body begins to deteriorate almost immediately. Bones lose roughly 1% of their density per month. Muscles, particularly those in the legs and back that normally work against gravity, can lose 10 to 20% of their mass within weeks. The heart, no longer needing to pump blood upward against gravity, begins to shrink and weaken. Fluid shifts toward the head, causing the face to swell and the legs to thin, a condition astronauts call puffy face and chicken legs. This redistribution of fluid increases pressure inside the skull, which in turn presses on the optic nerve. A condition known as spaceflight-associated neuroocular syndrome, or SANS, causes structural changes in the eye that can impair vision. Some astronauts have returned from 6-month missions needing glasses they did not need before they left. For a crew spending 7 to 9 months in transit, followed by time on a planet with only partial gravity, the risk is significant. The exercise equipment on a Mars transit vehicle will likely include a resistive device, similar to the Advanced Resistive Exercise device used on the International Space Station, which uses vacuum cylinders to simulate the resistance of weights. There will be a stationary bicycle and possibly a treadmill with a harness that pulls the runner toward the surface. These machines are loud. They vibrate through the structure of the spacecraft. They take up space and require maintenance. But they are among the most important pieces of equipment on the ship, because without them, the crew will arrive at Mars too weak to stand, too fragile to work, and too deconditioned to survive the physical demands of landing and surface operations. The rest of the day is divided between work and maintenance. There are systems to monitor, experiments to conduct, data to transmit. The spacecraft is a complex machine, and it requires constant attention. Filters must be changed, software must be updated, equipment must be inspected and repaired. On a Mars transit vehicle, where there is no resupply ship coming and no spare parts warehouse, the crew must be able to fix anything that breaks using only what they have brought with them. They will carry spare components, diagnostic tools, and even a 3-dimensional printer capable of fabricating simple replacement parts from raw material. Resourcefulness will be as important as expertise. Meals are another anchor in the day. Food in space is functional, but it is also deeply psychological. It is one of the few sensory pleasures available. Crew members on the International Space Station have consistently reported that meals are a highlight of their day, not because the food is extraordinary, but because the act of eating together provides a sense of normalcy and social connection that nothing else replicates. On a Mars transit, the food will mostly be pre-packaged, thermostabilized and freeze-dried. Shelf life is a major concern. Vitamins degrade over time, particularly vitamin C, B1 and folate, and meals that were nutritious at departure may be less so by month 6 or 7. Some proposals include a small growth chamber where the crew can cultivate fresh vegetables. Not enough to sustain them, but enough to provide an occasional salad, a handful of cherry tomatoes, a splash of green in a world of metal and plastic. The psychological value of growing something alive in the emptiness of space may be as important as the nutritional benefit. Outside the thin walls of the spacecraft, the radiation environment is relentless. We discussed this in part 1, but it bears repeating here, because the transit phase is the most exposed portion of the entire mission. On Earth, the planet's magnetic field and thick atmosphere deflect or absorb the vast majority of cosmic radiation. On Mars, there is at least a thin atmosphere and solid ground beneath your feet to block radiation from below. But during transit, there is nothing. The crew is suspended in open space, shielded only by the hull of their vehicle and whatever additional material has been placed between them and the void. Galactic cosmic rays, the high-energy particles that stream through the galaxy from distant supernovae, penetrate most shielding materials. They pass through aluminium, through water, through flesh and bone. When they strike biological tissue, they can break DNA strands, damage cells, and increase the long-term risk of cancer, cardiovascular disease, and cognitive decline. The damage is cumulative and largely invisible. There is no pain, no immediate symptom. The crew will not feel the particles passing through them. But each one leaves a trace, a small wound in the architecture of their cells, and over months these traces accumulate. Solar particle events, sudden bursts of radiation from the sun, pose a more acute threat. During a major solar storm, the crew would need to retreat to a designated shelter, a small, heavily shielded area of the spacecraft designed for exactly this purpose. These shelters might use water tanks, polyethylene blocks, or the crew's own food and waste supplies as additional shielding mass. The wait could last hours or days. The shelter is cramped, darker than the rest of the vehicle, and uncomfortable. But it is the difference between a manageable dose and a potentially lethal one. Current estimates suggest that a round-trip Mars mission would expose the crew to roughly 1 sievert of radiation, which is associated with approximately a 5% increase in lifetime cancer risk. As the spacecraft moves away from Earth, something subtle begins to change. The communication delay grows steadily longer. In the first days after departure, it is barely noticeable. A few seconds, perhaps 10. Conversations with mission control are still nearly real time, but the delay increases with distance. After a month, it may be 3 or 4 minutes each way. After 3 months, 8 or 10 minutes. At its longest, the one-way delay reaches 22 minutes. A question asked will not receive an answer for nearly 45 minutes. This is not merely an inconvenience. It is a fundamental change in the nature of the crew's relationship with everyone and everything they have ever known. Real-time conversation becomes impossible. Video calls with family are replaced by video messages sent and received with long pauses in between. The spontaneity of human connection, the ability to laugh at something together, to respond to a facial expression, to interrupt with a thought, to comfort in real time, is stripped away. What remains is something more like correspondence, thoughtful perhaps, deliberate, but lonely in a way that is difficult to prepare for. the operational consequences are equally significant and more dangerous. On the International Space Station, mission control is in constant communication with the crew. When an alarm sounds, Houston can see the same data the crew sees and can offer guidance within seconds. Ground controllers have access to vast databases, entire engineering teams, and decades of accumulated troubleshooting experience. On a Mars transit, none of this is available in real time. If a system fails, the crew must diagnose and respond on their own. They can send a description of the problem to Earth, but by the time expert advice arrives, 20 or 40 minutes later, the situation may have evolved far beyond the original report. A slow leak that was manageable at the time of the first message may be critical by the time the response arrives. This means the crew must become their own mission control. They must carry the knowledge to diagnose any system on the vehicle. They must carry the judgment to prioritize competing emergencies. They must carry the authority to make decisions that, on the space station, would be made by teams of hundreds on the ground. This requires a different kind of training, a different kind of confidence, and a different kind of trust, both among the crew members themselves and between the crew and the agencies that sent them. And then, once every 26 months, there is the solar conjunction. For approximately 13 days, the Sun passes directly between Earth and Mars, and radio communication becomes unreliable or impossible. During this blackout, the crew is entirely alone. No messages in, no messages out, just the hum of the spacecraft and the silence of the void. The psychological weight of that silence, knowing that for nearly 2 weeks, not a single human voice can reach you from outside this small metal container, is harder to plan for than any equipment failure. The psychological landscape of a Mars transit is unlike anything in human experience. Submarines come close. Antarctic winter-over expeditions come close. The Mars 500 simulation, in which 6 volunteers were sealed in a mock spacecraft for 520 days, came close. But none of these environments fully replicate the reality of being millions of kilometers from Earth, with no possibility of rescue, no possibility of stepping outside, and no possibility of ending the experiment early. On a submarine, the crew knows that the vessel can surface. In Antarctica, an emergency evacuation, while dangerous, is at least conceivable. In the Mars 500 simulation, the participants knew, despite the best efforts of the experimenters, that they could walk out the door if they truly needed to. On a Mars transit, there is no door. There is no surface to rise to. There is no helicopter that can come. The irreversibility of the journey is total, and this knowledge, this constant, quiet awareness that there is no way out, is a psychological pressure unlike any other. Researchers have identified a pattern that appears in many long-duration isolation studies. It is called the third quarter phenomenon. Morale and motivation tend to hold relatively steady through the first half of a mission, then dip significantly after the halfway point, before recovering as the end approaches. The dip is characterized by low mood, low motivation, increased irritability, and interpersonal tension. At the Concordia Research Station in Antarctica, where 12 people spend the winter in darkness at temperatures reaching -80 degrees, studies have documented similar declines in coping strategies during the midwinter period, corresponding to the third quarter of the expedition. Interpersonal dynamics become magnified in confinement. Small habits that would be ignored in normal life, the way someone chews, the sound of their breathing, a repeated phrase or gesture, can become sources of intense irritation over months. Studies of space station crews have found that tension between crew members is often displaced outward, directed at mission control rather than at each other. On a Mars transit with communication delayed and intermittent, this displacement mechanism may not function as effectively. The crew will need to manage their conflicts directly, openly, and constructively. But perhaps the most profound psychological challenge of a Mars transit is something that has never been experienced by any human being. It is called the Earth out of view phenomenon. Every astronaut who has ever flown in space has been able to see Earth. From low orbit, it fills the windows. From the Moon, it is a vivid blue marble suspended in darkness. Astronauts have described the sight as transformative, a cognitive shift known as the overview effect, in which the fragility and interconnectedness of life on Earth become viscerally apparent. But on a Mars transit, Earth will shrink. Week by week it will grow smaller. Eventually it will become just another point of light, indistinguishable from the stars around it. No human has ever experienced this. No simulation can replicate it. The psychological impact of watching your home disappear is entirely unknown. Countermeasures will be built into the mission. Private psychological consultations via recorded messages with trained counselors on Earth, journals, music, movies, virtual reality environments that simulate forests, beaches, open skies, carefully planned events and celebrations to break the monotony. The lighting system will maintain a circadian rhythm. Exercise will release endorphins. The crew will have been selected, in part, for their psychological resilience. But no amount of screening can fully predict how a person will respond to an experience that no person has ever had. The first Mars crew will be, in the most literal sense, psychological pioneers. Sleep in space is its own challenge. The absence of gravity means there is no comfortable position. Crew members sleep in bags tethered to the wall of their individual pods, floating gently inside the fabric. Without the weight of blankets, without the pressure of a mattress, the body never quite receives the signals that it associates with rest. Add to this the constant noise, the occasional alarm, the disrupted circadian rhythm, and the ambient stress of knowing that you are in a fragile vessel surrounded by vacuum, and it is not surprising that sleep quality in space is consistently reported as poor. Astronauts on the space station average about 6 hours of sleep per night, less than the recommended 7 to 8. Over months, this deficit accumulates. Cognitive function declines, reaction times slow, irritability increases. For a crew that must remain sharp enough to handle emergencies and operate complex systems, this slow erosion of rest is a quiet but persistent threat. Dreams may change too. Astronauts have reported vivid dreams in space, dreams of falling, of floating, of Earth seen from above. Some have described dreams in which they are back home, walking through familiar rooms, touching familiar objects, and the sadness upon waking, finding themselves still in the spacecraft, has been described as a kind of grief. The mind, deprived of new sensory input, turns inward. It processes, it replays, it invents. The dream life of a Mars transit crew is an unexplored territory, one that may reveal as much about the human mind as the journey itself reveals about the solar system. By month 5, the human body has undergone significant change. Bone density in the hips and spine has decreased by several %, despite the daily exercise regimen. Muscle mass has diminished. The cardiovascular system has deconditioned. The heart, pumping blood in a body that weighs nothing, has grown slightly smaller. Blood volume has decreased by as much as 10%. Red blood cell production has slowed, a condition known as space anemia. The immune system has weakened, reactivating latent viruses that the body normally keeps suppressed. Astronauts on the International Space Station have shown reactivation of herpes simplex, Epstein-Barr, and varicella zoster viruses during long missions. In the close quarters of a transit vehicle, where every surface is shared and the air is recycled, even minor infections become a concern. The spine has elongated. Without gravity compressing the vertebral discs, astronauts grow taller in space, sometimes by as much as 5 centimeters. This can cause significant back pain and increases the risk of disc herniation upon return to gravity. The fluid shift toward the head has flattened the back of the eyeball, thickened the retina, and altered the optic nerve. These changes, collectively known as SANS, affect a significant proportion of long-duration astronauts. Some changes reverse after return to gravity, some do not. The crew carries medications, anti-nausea drugs for the early days, pain relievers, antibiotics, sleep aids, minor surgical instruments and training, because a dental abscess or an appendicitis cannot wait for the return to Earth. An AI-assisted medical decision system that can guide the crew through diagnostic procedures and suggest treatments based on symptoms and vital signs. The crew are not doctors, though at least one will have advanced medical training. They're explorers carrying a pharmacy, hoping they will not need most of it. But if they do, they will have no one to call. The communication delay makes remote surgery impossible. Any latency greater than about 100 milliseconds renders real-time guidance from Earth impractical. The crew must be prepared to perform procedures on each other that, on Earth, would be handled by specialists in sterile operating rooms with full support staff. And yet, despite all of this, the crew must arrive at Mars ready to work. They will need to operate complex landing systems under extreme G-forces. They will need to walk, possibly in a spacesuit, on a surface with 38% of Earth's gravity. They will need to think clearly, move competently, and respond to emergencies. The transition from 7 months of weightlessness to the partial gravity of Mars is something no human has ever done. How quickly the body readapts, how well the muscles and bones and vestibular system respond to gravity after so long without it, remains one of the great unknowns of the mission. Studies of astronauts returning to Earth after 6 months on the space station show that readaptation takes weeks. But those astronauts return to full Earth gravity, with medical teams waiting on the ground. The Mars crew will arrive at partial gravity, with only each other. There is another dimension to the transit that is rarely discussed in technical papers, but that every person who has spent time in extreme isolation understands. It is the way that confinement changes the texture of time itself. The first weeks pass quickly. Everything is new. The view from the window is still recognizable. The routine is still being established. But as the weeks stretch into months, time begins to distort. Days feel identical. The distinction between Tuesday and Saturday dissolves. Without the natural markers that give time its shape on Earth, the changing of seasons, the rhythm of weekends, the arrival of visitors, the days blur together into an undifferentiated stream. Some crew members in long-duration simulations have described this as a kind of temporal flattening, a sensation that time has stopped moving forward and has instead begun to pool, stagnant and heavy, in the confined space of the habitat. Countermeasures exist, the structured schedule helps, milestones help. Marking the halfway point, celebrating when the delay drops below a certain threshold, tracking the growing size of Mars in the windows, these temporal landmarks give the journey a sense of progression. But the fundamental experience of living the same day, in the same space, with the same people, for more than 200 consecutive days, is a challenge that goes beyond psychology. It is existential. It asks the crew to find meaning in repetition, purpose in maintenance, and beauty in a view that does not change. The bonds that form between crew members during this transit will be unlike any other human relationship. These 6 people will share an experience that no one else in the history of the species has shared. They will know each other's habits, fears, strengths, and weaknesses with an intimacy that comes only from prolonged, inescapable proximity. They will have saved each other's lives, perhaps literally during equipment failures or medical emergencies. They will have seen each other at their worst during the low points of the third quarter and at their best during moments of competence and kindness and unexpected laughter. When they finally step onto the surface of Mars, they will do so as a unit, bound together by an experience that will define the rest of their lives. The question that shadows the entire journey is simple. What happens if something goes wrong? Not a minor malfunction, but something catastrophic. A hull breach, a fire, a medical emergency that exceeds the crew's training and equipment. On the International Space Station, the answer is always the same. You get in the lifeboat and you come home. On a Mars transit, there is no lifeboat. There is nowhere to go. This reality shapes every aspect of the vehicle's design. Redundancy is built into every critical system. Life support has backup systems. Power has backup systems. Navigation has backup systems. The vehicle is designed so that no single failure can be fatal. But the history of human spaceflight includes moments where survival depended on improvisation, on solutions that no engineer had anticipated. Apollo 13 in 1970 is the most famous example. An oxygen tank exploded 2 days into the mission, crippling the command module. The crew survived by repurposing the lunar module as a lifeboat, using its oxygen and power systems for a purpose they were never designed to serve. The engineers on the ground improvised a carbon dioxide filter from materials the crew had on hand, literally fitting a square peg into a round hole with cardboard and tape. The crew returned safely, but the margin was razor thin. On a Mars transit, there would be no lunar module to repurpose, but the principle holds. The crew must understand the systems deeply enough to devise solutions that are not in the manual, and they must remain calm under pressure not for minutes or hours, as in most emergencies, but potentially for weeks or months. Because a damaged vehicle on a Mars trajectory cannot return to Earth any faster than an undamaged one. The orbit does not care about emergencies. The physics is indifferent. If something breaks in month 3, the crew must live with the consequences and the repair for the remaining 4 or 5 months of the journey. This demands a kind of sustained composure that is rarely tested on Earth. Not the adrenaline-fueled calm of a crisis that lasts minutes, but the deep, deliberate steadiness of people who know that their situation is serious and that the resolution is months away. Fire is among the most feared scenarios. In the oxygen-rich enclosed environment of a spacecraft, fire behaves differently than on Earth. Without gravity to create convection currents, flames do not rise. They form spheres, feeding quietly on whatever fuel they find. Detection must be rapid. Suppression must be immediate. The crew trains extensively for fire response, because in a sealed vehicle millions of kilometers from help, a fire that is not controlled within minutes could be unsurvivable. The vehicle will carry fire suppression systems, portable extinguishers, and the ability to depressurize and seal individual compartments. But the crew knows, in a way that is difficult to fully internalize during training, that they are their own fire department, their own paramedics, their own everything. Throughout the transit, the spacecraft's position is tracked with extraordinary precision. Deep space network antennas on Earth, massive dish receivers stationed in California, Spain, and Australia send and receive signals that measure the vehicle's distance and velocity to within meters across millions of kilometers. The crew may also use star trackers, optical instruments that identify the positions of known stars and calculate the spacecraft's orientation against the fixed background of the cosmos. Mid-course corrections are planned into the mission timeline. These are small engine firings that adjust the trajectory to account for slight errors in the initial burn or gravitational perturbations. The first correction usually occurs within days of departure. Additional corrections may follow at intervals of weeks or months. As Mars approaches, the navigation becomes more critical. The final correction sets the vehicle on its precise entry path. Too steep an approach, and the vehicle will heat beyond its thermal limits. Too shallow, and it will skip off the thin atmosphere into deep space. The window between these extremes is narrow, and the calculations must be exact. After 7 or 8 months of emptiness, Mars appears. At first, it is just a point of orange light, brighter than the surrounding stars but not yet a disk. Then, over the course of days, it grows, features emerge, the dark patches of ancient lava plains, the pale sweep of Hellas Basin, the rust-coloured dust that gives the planet its name, and on the horizon of the approaching world, the colossal profile of Olympus Mons, a shield volcano 3 times the height of Everest, with a base the size of France. For the crew, this is the first truly new sight in months. The monotony of the transit is broken by something ancient and vast and real. Mars fills the windows the way Earth once did, but it looks nothing like home. There are no oceans, no green, no clouds of water vapour drifting across blue sky. What the crew sees is a world of stone and dust and ice, beautiful in its austerity, but profoundly alien. A world that has been cold and dry for billions of years, waiting in the silence of space for someone to arrive. There is a period of orbital preparation before the landing. The spacecraft may spend days circling Mars, adjusting its orbit, verifying the landing site, confirming that the cargo modules sent ahead are intact and operational. From orbit, the crew can see the landing zone. They can see the habitats, the power systems, the equipment that has been waiting for them, sometimes for years. It is a strange feeling to see your future home from above, to know that within days you will be standing on the surface that is currently passing beneath you at thousands of kilometers per hour. The anticipation is intense. The transit is over. The waiting is almost done, but the most dangerous phase is yet to come, and then comes the landing. Engineers call this phase Entry, Descent and Landing, or EDL. For robotic missions, it has been called the 7 minutes of terror. For a crewed mission carrying a vehicle many times heavier than any robot ever sent to Mars, it'll be the most dangerous 7 minutes of the crew's lives. The problem is Mars's atmosphere. It is roughly 100 times thinner than Earth's. A spacecraft arriving from interplanetary transit enters this thin envelope at tremendous speed, perhaps 20,000 kilometers per hour. The friction generates extreme heat. The heat shield will reach temperatures exceeding 2,000 degrees Celsius. Behind the shield, the crew feels the deceleration as a crushing force. The vehicle may experience 10 to 12 times the force of gravity in the span of minutes. After 7 months of weightlessness, this is a brutal shock for bodies that have been weakened by months of microgravity. The thin atmosphere slows the vehicle, but not enough. A parachute can reduce the speed further, but even the largest supersonic parachute ever built can only slow a heavy vehicle to a few hundred kilometers per hour. The final phase requires powered descent, retro rockets firing against the direction of travel. This technology, called supersonic retropropulsion, has been demonstrated by SpaceX on Earth, and NASA studied the data closely. But performing it on Mars, in a thinner atmosphere, with a much heavier vehicle, while dust kicked up by the engines potentially obscures the sensors, is something that has never been done. The entire sequence takes approximately 7 minutes. During those 7 minutes, the communication delay means that mission control cannot help. The vehicle's computer must execute the entire sequence autonomously, adjusting in real time to atmospheric conditions and terrain hazards. The crew can intervene if necessary, but the speed of events leaves little room for deliberation. And then, if everything works, the vehicle touches the surface of Mars. The engines shut down, the dust settles, and inside the spacecraft 6 people sit in silence, pressed into their seats by a gravity they have not felt in 7 months. There is a moment just after landing when nothing needs to happen. The checklist can wait. The surface operations can wait. For a few breaths, the crew simply exists on another world. They have crossed a distance that, at its closest, is 55 million kilometers. They have endured the launch, the silence, the radiation, the isolation, the physical deterioration, the slow disappearance of Earth, and the terrifying minutes of entry and descent, and they have arrived. Through the window, a landscape stretches to the horizon. It is the colour of rust and old brick and dried clay. The sky is not blue, it is a pale butterscotch, occasionally deepening toward pink at sunset. The sun is smaller here, about 2/3 the size it appears from Earth, and the light has a quality that is difficult to describe. Dimmer, colder, but still recognisably sunlight. Still the same star that has illuminated every human morning since the beginning of the species. Everything they need to survive is either inside the vehicle or waiting in cargo modules that landed before them, sent ahead during a previous launch window. Habitats, power systems, oxygen generators, food stores, all of it placed on the surface by robotic missions, checked and confirmed functional before anyone was asked to climb aboard a rocket and leave Earth behind. The crew will need time to readapt to gravity, time to let their vestibular systems recalibrate, their muscles remember what it means to bear weight. The first steps on Mars will not be graceful, they will be careful, halting, uncertain, but the body will adapt. It always does. In those first hours, as the crew sits in the landed vehicle and feels the weight of Mars pressing them gently into their seats, something else will happen that is harder to measure than bone density or muscle mass. They will begin to understand what they have done. Not abstractly, not as a line on a mission timeline, but viscerally. They have travelled farther from home than any human has ever been. They have endured months of confinement, monotony, physical decline, and psychological pressure. They have crossed an ocean of emptiness that makes every previous human journey seem small, and they have arrived somewhere genuinely new, not a different continent, not a different hemisphere, but a different world, a place where the air is not breathable, the ground has never been walked on, and the nearest other human beings are months away by the fastest route possible. The journey has changed them. 7 months of weightlessness has changed their bodies. 7 months of isolation has changed their minds. 7 months of watching Earth shrink to a point of light has changed their sense of who they are and where they belong. They are no longer quite the same people who climbed into the spacecraft on that morning when the engines ignited and the weight pressed them into their seats. They are something new, something that has never existed before. They are the first human beings on Mars. But that is the next chapter of this story. What the crew does in those first days and weeks on Mars, how they leave the vehicle, how they walk on ground that no human foot has ever touched, how they begin the work of living on another world, how they face the dust, the cold, the thin air, and the extraordinary challenge of making a home where nothing has ever lived. That story will be told in part 3, Life on Mars, where we will follow the crew through their first year on the surface. Thank you for listening to Streamberg Space Stories. If this journey meant something to you, consider subscribing so you will be here when the story continues. Part 3, Life on Mars is waiting for you. Until then, take care of yourself and keep looking up.